we all think of water waves, but there are other kinds. And most important to us, for practical purposes, are waves we can't even see. Sound, light and radio, for example. But all waves, visible or not, have certain features in common. The motion of each swing is like all the others, but each one is slightly out of step with those next to it, so a wave shape moves along the line. Waves are oscillations that are copied right down the line, each with a slight delay. A series of undulations seem to move along the millipede's body. It's rather the sort of thing we can get with a coiled spring. It's called a compression wave. This is a continuous compression wave. Concentrate on just one of the yellow bars and you can see that it simply oscillates to and fro over a small distance. This kind of wave is vital to each one of us, as we'll realize in just a moment. The cone of a loudspeaker. Sounds are made by things that vibrate. Here it is in slow motion. The influence of the vibration is carried through the air to our ears. Inside, the eardrum vibrates in response. But how is the sound energy actually carried through the air? Let's put a candle in front of the loudspeaker and switch on. Once again in slow motion. Notice the flame moves just as the cone does, so clearly the air itself must be moving to and fro. It's not hard to imagine that sound is carried by this sort of wave motion in the air. It's the compression wave we saw a few moments ago. All sounds are made by vibrations. A kitten's purr is caused by vibrations of its larynx. We can't see the larynx, the voice box, but we can see an electronic picture of the vibration using an oscilloscope. And this is a vibration picture of the human voice. My voice, in fact. Do, re, mi, fa, sol, la, ti, do. To get a clear idea of how this electronic picture is made, we'll look at a very simple vibration, a tuning fork. Let's see exactly what this vibration picture means. Seen in slow motion, this is how the tuning fork moves. And the spot matches the movement exactly. Now watch. The spot is moving across the screen as it goes up and down. And this shows that the speed of the movement sideways is steady. This is exactly what happens with an oscilloscope, but much more rapidly. This sound synthesizer at the BBC's radiophonic workshop can create sounds using electronics. The knobs can be set to give any pure tone that's wanted, and any mixture you care to imagine. now may I introduce Mr. Michael...
Ladies and gentlemen, your attention, if you please. It's my duty to bring to your notice a most curious phenomenon, the details of which will become clear to you in a very few moments. Now, the effect to which I refer is the strange sound of my voice. Now, it may not sound strange to you, because you believe that I am talking to you inside an auditorium. Whereas, in truth, I'm out in the open air. It's a trick achieved by electronically processing my voice. But why should the same voice sound different inside and out? Because outside, there are very few surfaces which will reflect the sound waves back towards me, producing echoes and reverberations. But inside, the very opposite is true. Most rooms have at least 4 walls, a floor, and a ceiling, and all of these are surfaces capable of producing echoes and reverberations. But this is a room which has no echoes. Reflective surfaces, its floor, its walls, and its ceiling have all been covered with special sound-absorbing plastic foam wedges. This is an anechoic chamber, a dead room. They use it for testing sound equipment like loudspeakers. Because when you're making a really accurate sound test, you want to hear only the sound that comes directly from the loudspeaker. You don't want to hear echoes and reverberations from the reflective surfaces. Now, we've borrowed the anechoic chamber for a demonstration. We're to use sounds to create silence. Across the other side of the chamber, there's an identical loudspeaker, switches, and I'll position myself midway between the 2 loudspeakers. Now, this microphone is the only one operating in the dead room. Through it, you're hearing my voice and anything else that happens here. This control circuit enables me to switch on first one loudspeaker, then the other. Now, listen. Do you hear that quiet patch? Now, the microphone is still working because you're hearing my voice through it, but there is certainly a spot here where the sound almost disappears. Whereas over here, it's comparatively loud. I'll switch off both loudspeakers. Now, I'll try very much the same sort of thing, but this time, I'll start a good deal closer to one of the loudspeakers. Here we are. Switch on. 1, 2. Now, all I'm going to do is walk very slowly towards the other loudspeaker. Switch off. Very strange. All along the path between the 2 loudspeakers, there appear to be loud, quiet sections, and they seem to be regularly spaced out. Absurd. But this is only one of the strange possibilities that exist as a result of sound being sound waves. In certain circumstances, identical sound sources can produce waves which cancel each other out. Let's try and see how such things come about. This is a clue, something you may have seen, a cup of tea that's picking up vibrations. Notice how the circular ripples seem to be almost standing still, an example of what scientists call standing waves. Here's one way they can come about.
If waves are sent down a rope in both directions at once, something slightly unusual occasionally results. This, in fact, is a standing wave. Now, the wave obviously isn't actually standing still, but there are places where there's almost no movement at all, just a sort of swiveling. And if we freeze the picture, we can see that these places are exactly half a wavelength apart. Now, if these were sound waves, the places with no movement would be the quiet patches in the anechoic chamber. But in reality, remember, sounds are compression waves, and this picture represents a standing compression wave. Notice that here there's almost no movement. And no movement here. Once again, the places where there's no movement are like the quiet patches in the dead room. Now, for those who want to puzzle out the details, here are the figures. Distance between the quiet patches, 0.5 meter. Frequency of the sound, 343.
I'm driving along the M4 motorway from London to Bristol, and there's something very strange on the radio. There's nothing wrong with the program, but listen for yourself. Did you hear that? It went quiet. Listen a little bit longer. There, it's got louder again. Now it's been going loud, quiet, loud, on and off for the last couple of minutes or so. The quiet patches come approximately once every 6 seconds. I know that there's nothing wrong with the radio, and I'm sure that the BBC engineers at the transmitter aren't altering the level of the power. So what is happening? Let's check on some details. First of all, the way the radio is behaving, the loud and the quiet patches, sounds remarkably like what happened in the dead room, the room which has no echoes. But I'm driving along the motorway at something approaching 65 miles an hour, so clearly the quiet patches are in this case a good deal further apart. And there's another difference, an important difference. I may be hearing sound from the radio, but the radio itself isn't picking up sound, it's picking up radio signals, which it converts into the sound that I can hear. So, though I may appear to be driving through patches of loud and quiet sound, what I'm really doing is driving through patches of strong and weak radio signals. Now, the radio was tuned to BBC Radio 4, and the key to the mystery is this. There are 2 Radio 4 transmitters in the south of England, which I can pick up from here. One of them is close to Bristol, the other one much nearer London. 200 kilometres separate them. But they work rather like the loudspeakers in the dead chamber, even though 200 kilometres are between them rather than just a few metres. Radio waves instead of sound waves. Radio transmitters instead of loudspeakers. 200 kilometres rather than just a few meters. The effect, though, is...
Here are the details. Speed, 29 meters per second. Time intervals, 5.7 seconds. Radio 4 wavelength, 330 meters.
It's easier to go straight across. That was fun. I haven't had any trouble. Okay.
One extraordinary thing about radio waves is their speed. Messages from astronauts on the moon take a mere 1¼ seconds to reach us. Another fact, the time it takes light to reach us from the moon is precisely the same.
And that's no coincidence, because radio and light are both waves. But what's perhaps more surprising, the same sort of waves. They're electromagnetic waves. They're the wave effects of electric fields and magnetic fields. But put it at simplest, that means that they travel at the same speed, the speed of light, and they're capable of traveling through empty space. They're not like sound waves, for instance, which need something to travel through. Air, for example. So if light and radio waves are the same sort, what are their differences? Because you can see light, you can't see radio. The most crucial difference between the two is their wavelengths. The wavelength of radio waves can be as long as a football pitch. The wavelength of light waves is very, very short. The light you're watching on your television screen at the moment has a wavelength of around a 20,000th of a centimetre. That means 20,000 of those waves would stretch for a distance equal to that side of the pen top across to that side. So if light does consist of waves, are there any odd effects, like the one we discovered with radio waves on the M4, the loud and quiet passages on the radio set? Well, if there are any such strange effects, they occur on a very small scale indeed. Consider this needle. If I use an ordinary slide projector, I can produce a highly magnified shadow picture of the eye of the needle on that screen. There it is, clearly defined. Not too much to that, exactly what you might expect. But now, let's try exactly the same thing, this time using a laser. A laser is nothing more than a lamp which produces very pure light, unlike the white light from the slide projector, which is actually made up of all the colors of the rainbow. Now, in front of this laser, we've mounted an identical needle, right in the path of the laser beam. Let's see what sort of a shadow picture the laser casts. If light travels in, how do you explain a shadow like this? Because lasers consist of minute waves.